Welcome to this edition of Quick Takes, short bites on medical statistics. These short videos, are meant for medical students, postgraduates, and doctors who are interested in medical statistics but are generally scared of numbers and math. In this edition, we will talk about the emerging concepts in what we call as correlation in statistics. In medical statistics, correlation means relation between two data sets as to how two variables are related to each other at different levels. Let us look at an example. Let's say I tell you that eating chocolates causes hip fracture. Second statement, high blood pressure causes stroke. And the third, high HDL cholesterol prevents myocardial infarction. Obviously, the first statement is not right, while the other two are right. Now, let us look at how graphically, from the medical statistics perspective, this data would look. For example, if you look at this graph on the right, eating chocolates in the x-axis, hip fracture in the y-axis, we see all the data points are scattered all over the ground, which means each data point is different. There's no clear relationship between eating chocolates and hip fracture. Now let us look at something else. The second point we talked about, blood pressure in x-axis and stroke in the y-axis. Here we see, unlike the chocolate and hip fracture, there is a clear linear relationship between the points. As blood pressure increased, the stroke tended to increase. But there is a positive correlation. Now the third point of HDL in the x-axis and myocardial infarction in the y-axis. Again, there is a clear correlation, but it is going down, a negative correlation. So what are we talking about? In medical statistics, when we talk about correlation, we have a positive correlation, we have a negative linear correlation, and a situation where there is no correlation at all. The points are all scattered. Right. So this means that when we are talking about these three statements, we say that eating chocolate doesn't cause hip fracture, blood pressure causes stroke, and HDL cholesterol prevents MI. Right? Wrong. Absolutely wrong. Because when we talk about correlation, we just talk about two data sets correlating with each other. That does not go and tell us that there is a cause and effect relationship. Right? Which means correlation is not causation. There may be relationship between blood pressure and stroke, but that doesn't mean that by a good correlation, blood pressure in these graphs are responsible for stroke. So, correlation data set, what we saw here in the graphs, indicate that eating chocolates don't correlate with hip fracture. Blood pressure correlates positively with stroke. HDL cholesterol negatively correlates with myocardial infarction. Not necessarily that these are reasons why a stroke or a myocardial infarction happens. Right, so correlation, remember again, doesn't mean causation. Okay, now how do we rate correlation? We rate correlation by a small letter r, which is called a Pearson correlation coefficient, r. Now if we have a perfect positive correlation, a linear, strong positive correlation, we call it 1 plus 1. a negative correlation is -1, while no correlation scattered all around is 0. Right, so let us look at some examples. Here in the x-axis we have mean height in centimeters, and let us say y-axis we have myocardial infarction. Unrelated. A tall or a short man can both get myocardial infarction, right? So the graphs are scattered all over. So the R value is 0. No correlation at all. Okay. Now look at a different example. X-axis LDL cholesterol. Y-axis myocardial infarction. Exactly like we saw before, they are very linearly correlated. Right. So the R value here, as you see, is 0.9. Good correlation. Close to 1. Now look at the third example. X-axis is HDL cholesterol. Y-axis myocardial infarction. And if you draw a line, it is negative linear correlation. R value 0.8, again close to 1. Right. So what are we talking about? We are talking about a spread where right to the left you have, extreme left, you have a positive correlation, small r value is +1. On the extreme right side, you have negative correlation, r value of -1. They are perfect correlation, perfect positive and perfect negative correlation. Generally in statistics, it doesn't happen. While right in the center, you have diffuse scattered dots, no correlation at all, and an R value of 0. In between this extreme of 1 and 0, on the left and right, you can have 0.8, which is called highly positive correlation, 0.3, low positive correlation. And between 0 and -1, you can have -0.3, low negative correlation, -0.8, highly negative correlation. Right, so you have a spectrum from 1 plus to -1, 0.8, 0.3, -0.3 and -0.8 on the sides and 0 right on the center. So that is the entire scatter there. So in statistics, we want it to be somewhere 0.8 to 1 or -0.8 to -1. And we classify the values like this. So if you have something more than 0.8, strong. Right. If you have something between 0.5 and 0.8, the correlation is median. And if you have something which is less than 0.5, it is weak correlation. And as we saw, 0, no correlation. So now we know the values of correlation, different grades. Now, and of course, we need to look at a p-value of 0.05, which tells us, yes, that there is a significant p-value and the results are not just a matter of chance. Now from correlation, we move on to something which sounds very familiar and similar, but it is called regression. Right. Now in regression, unlike correlation, correlation is a relationship between two variables, but regression is a tool. Like that ruler there, it's a tool. It's a tool that tells us that if we have one of the variables available to us, can we predict the other variable? So regression gives us the ability, a tool, to predict one variable when we have value of the other variable, and that is regression. Let us look into regression a little more details. Let's say this graph, you have x-axis of LDL cholesterol, we have already seen that. The y-axis is myocardial infarction rate, and the scattered points are there. Now let us say we draw a best of fit line of these dots, and the best fit line looks like the red line there. Right. So what you see, the red line has cut the y-axis above 0. And that gap between the baseline and the point where the y-axis is cut is that gap of red arrow, which is called A. Right, A. Now the slope of this line is B. Okay, now if we know the A and the B, we can try to predict the value of y by an equation of A plus B into x. X is the value of the x-axis. So if we have the value of x-axis multiplied by the B slope and we add up the value of A, we can predict y. Yeah, logical, right? So we are looking at the x-axis value, draw a straight line, hit the B slope there, multiply the value of x with the slope rate and add up A, we get y. So basically, a regression equation is a tool that helps us guess and predict the value of y, here the myocardial infarction rate, by looking at a value of LDL cholesterol, which is in x-axis. So again, a regression equation is a tool that gives us the power to calculate one variable when the other variable is available. Right. So tips and tricks. Number 1, R value in correlation closer to 1 is strong. 0, no correlation. Second, understand that in correlation, we just say that the two data sets are correlating. Not necessarily one is responsible for causing the other. The p-value needs to be 0.05 to say that the correlation is significant. And remember, regression is a tool that gives us the ability, by looking at an equation, to calculate one unknown variable when we have the other variable known. Right. Also, don't forget that both in correlation and regression, the sample size needs to be sufficient. Just because I've calculated 10 patient data and made a plot doesn't mean anything. And generally, a rough rule of thumb, the sample size needs to be more than 150 for any data to give us a confident result of a correlation. With that, thank you for your attention and stay tuned for such further videos.